This is the first lecture of Advanced Chemical Reaction Engineering CHE 510 of the Middle East Technical University Chemical Engineering Department. So the name of the course is Chemical Reaction Engineering. I will divide the topic into two and address those two terms, chemical reaction terms together and engineering terms separately, and then I will link them together. Chemical reactions require bond-making, bond-breaking events. Traditional understanding of chemical conversions imply doing the reaction in a test tube or in an Erlenmeyer flask. When we take these chemical reactions and translate it into the engineering domain, we carry out the events on a large scale, such as millions of tons, depending upon the commodity, millions of tons per day or millions of tons per year, and we carry out these events in continuous units. By continuous units, I mean that the unit as a black box is continuously fed by the reactant and the products are continuously removed from the system. Now, those continuous units are in an undergraduate chemical reaction engineering course classified as plug flow reactors, where we have a tubular domain where feed enters and the product leaves, and we have no radial mixing in the reactor. The fluid package moves in the reactor as if it were a plug. So this is the plug flow reactor, PFR. Or this reaction can be carried out in a continuously stirred tank reactor, CSTR, where we have an impeller to mix the contents of the reactor. Feed comes in, products leave, and the contents are well stirred. Continuously stirred tank reactor. So the difference between the laboratory scale and industrial scale the difference between those two are important to address. In the laboratory scale reactors, the scale is really small. For example, the diameter of this test tube is about 1 centimeter. So the contents, if they are in a heat bath, can be considered as isothermal. In other words, there are no temperature gradients. And if you are carrying out this reaction in an Erlenmeyer flask, maybe you have a magnetic stirrer mixing up the contents so that you have mixing in all directions. And because of these mixing, we have, in addition to no temperature gradients, we have no concentration gradients. Given this, that these systems allow us to determine the constitutive relationship between the concentration and temperature and the reaction rate. In the absence of temperature gradients and concentration gradients, we are able to obtain the constitutive relationship of the reaction rate minus R sub A for a hypothetical A goes to products reaction as K times Ca, where Ca is the concentration of species A. And K relates in Arrhenius form the rate constant to reaction temperature through the activation barrier, the universal gas constant, and the temperature in the Kelvin scale. So this constitutive relationship is an empirical relationship. N is the order of the reaction, K is the rate constant, and minus Ra is a constitutive relationship. And we assume that there are no temperature and no concentration gradients under the conditions. But on the other hand, when we arrive at the industrial scale of operations, in order to produce millions tons per year or per day, depending upon the nature of the commodity, we have to operate large-scale units. In those large-scale units, we can have concentration gradients. In the industrial scale, concentration gradients. Temperature gradients. And also, flow inhomogeneities are possibilities. All right, you have to deal with those issues. Now, on this side, where we are carrying out the chemical reactions, we eliminate the gradients, or we assume that those gradients do not exist. In the industrial scale, we have to deal with those gradients, and in this course, our learning progress will evolve where we are going to remove assumptions one by one from the conservation equations and solve processes and design equations in order to, number one, size the reactors, number two, operate those reactors under such conditions that we have highest selectivity and perhaps highest activity. Okay, so let me take a break. Okay, let us continue with the problem of these gradients, concentration gradients, temperature gradients, and flow inhomogeneities. Every chemical engineering problem requires some solution of a conservation equation. In the chemical conversion problem, we solve the conservation of mass. When temperature is our concern and we wish to find out how the temperature changes in the domain, we solve conservation of energy. And in a flow domain, in order to find out flow behaviors and rates, we solve the conservation of momentum equation. Which problem to solve depends on what is the objective of the problem and which problem to ignore requires a good understanding of the issues. So let us take an industrial scale plug flow reactor. That feed comes in, and product leaves. Now we are writing these balance equations for this hypothetical A goes to product's reaction. Our plug flow reactor, the idealized plug flow reactor, on this side of the board, the fluid element was moving as if it were a plug. In other words, we had no radial mixing in this reactor. If the diameter of the reactor is large enough to give rise to gradients in temperature and gradients in momentum, we might have velocity profiles as well as temperature profiles. Now, in this hypothetical reaction, it seems like the temperature is decreasing along the reactor. T of R, and this is of course V of R. Now ask yourself, if the temperature is decreasing along the radius, whether this is an endothermic or an exothermic reaction, right? So there's a question here, is this reaction endo or exothermic? So if we are sure that we have velocity gradients and temperature gradients, it is important that we have to solve the momentum balance and the energy balance along with the mass balance or species conservation equation. In order to have an accurate representation of the reactor behavior. in a continuously stirred tank reactor, this was a plug flow reactor. In a continuously stirred tank reactor, we have an impeller mixing a liquid domain. Our hypothetical reactant A enters. Unconverted ones leave. But if our reactor has imperfections in terms of heat transfer, imperfections in terms of mixing, we might end up losing our uniformity assumptions. Now let's see what can happen. If this reactor is externally heated using a heat mantle or serpentines, we are going to have an external temperature provided here, and if there are imperfections in the mixing, we will have gradients of temperature that is going to have R versus T functionality, as you would see. In other words, here in this reactor, our temperature is decreasing from the wall to the interior. Now again, the same question, is this reaction endothermic or exothermic? The second thing is that we might have an imperfection in terms of mixing. If our impeller is not functioning well, we may be able to mix the domains that are close to the impeller well. However, domains outside may remain stagnant. Under such conditions, we may not be able to use the uniform concentration assumption as we have been using in the lectures when we were teaching you this subject as an undergraduate material. Therefore, we have to solve again mass balance, energy balance, and momentum balance simultaneously. However, solution of those three conservation laws simultaneously are non-trivial problems. And first of all, we have to learn how to analyze a problem, how to eliminate the limitations, and how to arrive at a conclusion, at a solution as quickly as possible and as close to the reality as possible. Now, of course, when we discuss about problems requiring solutions of conservations of mass, energy, and momentum simultaneously, we need a structure in problem solution. So first of all, we have to identify the problem. We have to identify what we know, what we do not know, and also we have to identify what we can include in the analysis and what we can ignore without loss of much of the generality. So we're going to learn about the structure of the problem solution. Okay. The structure of the problem is reflected on the side of the board. That we have a reactor that is no longer operating under ideal conditions. That is a non-ideal reactor with velocity gradients, temperature gradients, and concentration gradients. How are we going to relate it to conservation laws, and how are we going to solve these problems? Now, first we have to identify, of course, the bottleneck. What is your bottleneck? Then we have to identify which conservation laws do we need. And we have to identify which parameters are available and which parameters we need to estimate. All right. Once we identify those, we start solution of the problem. Now let us remember the fact that we need to set boundaries in order to solve problems, and let us plot our system potato the hypothetical arbitrary system boundary that we have set around our problem, and we have inlet and outlet streams that is flowing through this system boundary. Now, this hypothetical system potato may refer to one reactor unit, like the ones we have on the other side of the board, or may refer to multiple reactor units, or may refer to a part of the reactor unit. But here, our scale is a macroscopic. Our length scale can be measured in terms of meters. Right? That's macroscopic. Then we are going to look at the interior of this system boundary. The frame that I cut, of the hypothetical frame I cut out of the system boundary, is of the millimeter scale. And in that millimeter scale, we have bubbles, we have pellets, and we have combustion domains, for example. In those pellet domains, let's magnify. We're going to have, if this is our pellet, solid pellet, representing the solid reactant, or solid pellet representing a catalyst. We have pores going through this pellet, connected or independent. Right? The diameter of these pores are of micrometer scale. And if we magnify those pores, let us take one pore and magnify it. Onto these pores, we have catalyst particles, which are of nanometer scale. On these catalyst particles, the nanometer scale catalyst particle in the micron scale pore has angstrom scale sites over which our reaction A going to B take place. However, A adsorbs onto the surface, becomes A star. The reaction can proceed forward and backward, and this A star converts to B. This reaction also proceeds forward and backward. And of course, we have this A to B reaction going in both directions in the microscopic scale catalyst pore. However, we have to take into consideration the fact that B can migrate back and forth in this pore, as well as A can migrate. Therefore, in this macroscopic reactor, while we might have a concentration that is a C and a temperature that is T that represents the bulk, we might have a different concentration given by C prime, different temperature given by T prime, that is on the millimetric scale of the catalyst, that is averaged out, which might be different from the concentrations that we encounter within the pores. Let me call this C double prime and T double prime. And to which precision that we are going to estimate those concentrations and those temperatures is going to be the topic of this course. So in the next section, I will be discussing the length scales, time scales, and the details. I will summarize this picture as a table for your reference. We are going to discuss time and length scales that we are going to encounter in a reactor. In the previous video, we have seen the pellet, the pore, the particle, the active site in relation to the reactor. So let us scale them in terms of their dimensions, in terms of the time scales of the events that take place. What are those processes, which equations we are going to solve, and what are our examples? All right, now first of all, our dimensions of the reactor, if you remember, was of meter scale. The dimensions of the pellet was of millimeter scale, or 10 to minus 3 meters scale. The dimensions of the site of the order of nanometer scale, or 10 to minus 9 meter scale. Coincidentally, we have similar timescales of the events that are taking place on the site, on the pellet, and in the reactor. Now, on the site, the processes that are taking place are bond-making, bond-breaking nature. And those events take place on timescales that are less than 10 to minus 9 seconds. On the pellet scale, the events that take place are of the nature of molecular migrations or diffusion. And the time scales of these processes are of the order of 10 to the minus 3 seconds. On the reactor scale, we have transport processes at the large scale. We have hydrodynamics. We have heat transfer. And we have macroscopic scale mass transfer issues. And of course, the timescales that are relevant in the reactor are of the order of second timescales. Now, which equations do we need to solve in order to have a grip of these events? Now, bond-making, bond-breaking events require electron transfer, and we have to solve Schrödinger's wave equation. All right. And of course, it's one of its many approximations. In the pellet scale, when we are bound to understand the molecular motions and the transport events, we have to solve species conservations. In the reactor scale, in addition to the species conservation equation, we need to solve the conservation of energy and conservation of momentum equations wherever needed. Now, let me give an example to the site, to the catalytic site, catalytic active site. It is, for example, platinum or platinum rhodium catalyst that cleans up the exhaust emissions, or it is the enzymes in biological systems that initiate chemical conversions. A typical pellet is the monolith, where you have those platinum or platinum rhodium catalysts. It has a millimetric openings, multi-channel system, or it is a spherical pellet which has a millimetric diameter with impregnated catalytically active materials. So we have millimetric scales. Corresponding example for the biological systems are, for example, organelles. So, and of course, at the reactor scale, our example is a typical industrial scale reactor. Or your exhaust muffler that resides underneath of your car. The corresponding reactor domain for the biological systems can be considered as a cell, a plant cell, or an animal cell. So if you summarize, we are going to learn to relate problems that are relevant at nanometer scale to the operations that are going to take place in meter scale. We're going to learn to relate events that are taking place at time frames shorter than a nanosecond to the macroscopic events that are taking place on the order of seconds. In doing so, we will relate the output of the Schrödinger's wave equation to the output of the conservation laws. So this is going to be the frame of the semester of this course.